Hello friends, welcome back to the channel. And in this video, we are going to see remarks on version space and candidate elimination. I hope you have saw the last two previous videos on version space and candidate elimination algorithm. If you have not, then please check out the playlist on our channel and watch those videos first. Then only you will understand this topic, otherwise you will not understand it. So I request you to search for machine learning playlist on our channel, that is friends explanation channel, and then you can find the playlist there and just follow the playlist. Before this video there are two videos which are version space and candidate elimination algorithm. These are detailedly explained, so you can watch those videos in this playlist. And yeah, talk too much. Now let's understand this. What are the remarks on our version space and candidate elimination algorithm, which we have learned in our previous videos? So this robot is really cute, na? I found this image on internet and I kept it over here because I felt this is so innocent and cute robot. So let's go to the next slide. Version space. What is version space? Let's do a revision. The version space, also known as the version set, is a set of hypotheses or models within a hypothesis space that are consistent with the observed training examples. It consists of all hypotheses that have not been ruled out by the training data. That means version space is containing all the hypotheses which are matching with the training data or which are consistent with the training data. And I gave you an example in previous video, like when we are teaching a small child how a cat might look like. So after giving the images to the child, see, this is how cats look like. So according to the hypothesis that we have fed earlier and the images that the child now he or she is seeing, according to the hypothesis, the child will filter out the images, right? And so this is like that. So according to the hypothesis, if the training data or training example is consistent, then that hypothesis will remain in the version space. So that is what version space. In simple terms, the version space is like a zone of uncertainty where multiple hypotheses coexist, each being a candidate for the true hypothesis that generated the data. As more data is observed, the version space can shrink, and ideally it should converge towards the true hypothesis. So as we saw the candidate elimination algorithm, we were shrinking out the hypothesis, right? We were comparing the hypothesis with previous examples, we were comparing the present hypothesis with present examples also to eliminate if the hypotheses are inconsistent, right? So we were shrinking out the hypotheses. So that is what the sentence is saying. Now let's go to the next slide. What is candidate elimination algorithm? So candidate elimination algorithm is a concept learning algorithm that maintains two sets of hypotheses, a most specific hypothesis and a most general hypothesis. It iteratively refines these hypotheses using observed training examples, eliminating hypotheses that are inconsistent with the data or the example. The result is a version space of plausible hypotheses that can specify new examples. So, this candidate elimination algorithm maintains two hypotheses, that is most general hypothesis and most specific hypothesis, and according to the example which is positive or negative example, these two hypotheses fits itself and it gets modified according to the operations that we are performing on the hypothesis and the examples. So that is candidate elimination algorithm. And we do all this candidate elimination algorithm steps to make a version space. Okay, now these are the remarks. First is version space as a representation of uncertainty. Then hypothesis space reduction. That means we are going to reduce the hypotheses. Handling noisy data. if there is a noisy data or incomplete data in our data set, then it is going to handle that. Incremental learning, that means if the machine learning gets new examples, then it is going to create the next version space. Convergence to a single hypothesis, that means we are going to shrink out the hypothesis, and we are going to we want it to become one hypothesis only, so that's why we are shrinking it. Next are complexity and computational resources. That means this candidate elimination algorithm is really simple, right? So we try to use it for complex things also. And next is applicability beyond binary classification. That means we are classifying the examples, is it positive or is it negative, and according to its classification we are performing some operations. So here, this can be beyond this positive and negative classifications also. That is what applicability beyond binary classification. Next is trade-off between specificity and generality. That means we are working with both specificity, I mean the most specific hypothesis, and generality, that means most general hypothesis. Next is educational tool. So this candidate elimination algorithm is used as an educational tool to educate the machine learning models to recognize things in the real world by using this algorithm. And real world applications, so let's see all of this one by one. Version space as a representation of uncertainty. Version space provide a structured way to capture uncertainty in machine learning. They allow us to maintain a set of hypotheses that are consistent with observed data, reflecting the range of possible explanations. So here, this version space is providing us such kind of structure which will uh, which will recognize all the uncertainty, right? They allow us to maintain set of hypotheses that are consistent. That means we are matching with the examples. Is this hypothesis consistent with this example or not? Then only we are retaining that hypothesis, otherwise we are removing it, right? So next one is hypothesis space reduction. The candidate elimination algorithm uses version space to iteratively reduce the hypothesis space based on observed examples. As I said, we compare the example and the hypothesis. Are they consistent? Then we will retain it. If they are not consistent, and also I told you a rule in previous video, that if the hypothesis and the example is getting compared, if the example is positive and the hypothesis and example both are matching, then we will retain it. Otherwise, if the example and hypothesis are not matching and the hypothesis is positive, then we will remove this hypothesis. And if we consider a negative example and a hypothesis, now we compare it. If the hypothesis and the negative example are matching, then it is an inconsistent, right? The hypothesis is inconsistent, so what we will do, we will create more hypothesis. And now if this the negative example and the hypothesis both are matching, then they are consistent, so we will retain that hypothesis as it is. It maintains both the most specific and most general hypotheses that are consistent with the data. So now next one is handling noisy data. So version space can be especially useful in handling noisy or incomplete data. They provide a mechanism to account for data imperfection by maintaining multiple plausible hypotheses, which is hypotheses that are consistent with the observed data. This plausible hypothesis means the hypotheses that are consistent with the observed example or the observed data. Now let's see next one, which is incremental learning. So as I said, that if the machine learning is seeing more examples, it will update its version space, right? So let's read out this. The candidate elimination algorithm incrementally builds the version space as new example arrives. It adapts to new information, either refining or extending the set of consistent hypotheses. So that is incremental learning. Next one is convergence to a single hypothesis. Ideally, as more data is observed, the version space should converge towards a single hypothesis that actually describes the underlying concept. However, this convergence is not guaranteed, especially in the presence of noise or insufficient data. So now here what we want is we want to converge the hypotheses, but sometimes it is not possible because of noisy data or incomplete data. So after doing all these steps that in a candidate elimination algorithm, we get two hypotheses, specific and general, which may be same, which may not be same. Sometimes we get same hypothesis, sometimes we don't get same hypothesis. So the main aim is to get a single hypothesis. Now let's go to the next one, complexity and computational resources. The size and complexity of version space can grow significantly with the size of the hypothesis space and the number of attributes. Managing version space for large datasets or complex problems can be computationally expensive. That means if the number of attributes increases and the number of hypothesis space also increases, then the complexity of that data processing will also increase, right? And according to that, it will become more expensive to learn all the data and to do predictions according to that fed data. So that is written in these lines. The next one are applicability beyond binary classification. So, while the candidate elimination algorithm is often presented in the context of binary classification, that is positive or negative, it can be adapted for multi class classification also. So, as I said, we are going to classify our examples with positive or negative, but here it is also possible to classify it in multi class by doing multi class classification. Next one is trade off between specificity and generality. So, the candidate elimination algorithm maintains a balance between the most specific and most general hypothesis. It aims to find a solution that is neither too specific nor too general. So here we are working with two hypotheses. One is general and one is specific. So according to the example, these both are fitting and they are adjusting. So that is what it is written here. The next one is educational tool. Version space and the candidate elimination algorithm are commonly used in educational settings to introduce concepts of machine learning, hypothesis space, and uncertainty. Last one, real world application. While the algorithm itself is somewhat simplified, the concept of version space has inspired more complex and practical algorithms in machine learning, such as Bayesian inference and ensemble methods. So, these two are very complex things, and as this candidate elimination algorithm is very simple to implement, that's why they are trying to use this algorithm and perform these two things using this algorithm. So summary, overall version space and candidate elimination algorithm are foundational concepts that help us understand how machine learns from data, handle uncertainty, and make predictions based on observed examples. They serve as building blocks for more advanced machine learning techniques and are valuable tools for teaching and understanding the field. So, this is what version space and candidate elimination remarks are. So, yeah, that's it for this video. And if you want to revise it once, let's see. First, we have version space as representation of uncertainty. Then it is that we want to reduce the hypothesis space. Then it is useful in handling noisy data also. And the version space gets updated as it says new example. The next is we want to converge both the hypothesis, that is specific and general hypothesis, into to become one hypothesis only, because we don't want too many hypotheses to consider, right? And next is complexity and computational resources. So as complexity increases, the expenses of performing that operation also increases. Applicability beyond binary classification. So examples can be classified positive and negative, and beyond that it can be classified, so it can be multi-classified also. Next is trade-off between specificity and generality. So we work with both most specific hypothesis and most general hypothesis. Educational tool, so it is used in different kind of machine learning models to train them. Real world applications, so these are used in also complex things like Bayesian inference and what was it, ensemble methods. So that's it. Whew. That's it for this video. If you liked my explanation, then please click that like button and subscribe to my channel for more such videos. And yeah, thanks for watching.